Hi everyone. So in this video I'm going to go over practice quiz 3 for the Organic Chemistry 1 lab, which mainly covers stereochemistry, and it also covers liquid-liquid extraction. So it says, which of the following is 2R3S23 pentane diol? So we have two alcohol groups attached to a five carbon chain. So it's a pentane diol, di meaning two alcohols, and then circle your answer. So when I'm doing this, the thing that you need to notice is there's a big hint here because you have this wedged OH here and this wedged OH here, is that what's not shown. So if we look here, we have a CH3. If we look at this carbon, we have a CH3 attached to it, this group attached to it, and an OH attached to it. Since carbon must have four bonds, there's also something else attached to this, and what else is attached to this is a hydrogen. Because only two atoms can be in the plane, specifically this carbon and this carbon chain, the OH is sticking out at us. That's what the wedge bond means. It means the hydrogen must be on the dashed bond. Similarly, here, this carbon has this ethyl group, this group, and the OH, which means there must be a hydrogen sticking back. Now, I'm not just picking this one because it's first. I'm picking this because if I know that if the OH is sticking out, the hydrogen's sticking back. And it's easiest to identify R and S based on the H sticking back. I don't have to invert anything in my head. I don't need to redraw it or any of this kind of stuff. So I'm going to pick this one and figure it out. Note that if it's not R and S, then I know the opposite is. So for example, if this one were to come out to be S, then I would know this one would be R, because it's the opposite. So if it's the opposite, it has to have the opposite chirality. So let's take a look here. We need to sign the priority groups, and what I want to do is sign the heaviest group to be the 1. So if I look here, the lightest group is back. That's important because the lightest group is the hydrogen. So I have this 1. Now, this is 1 because oxygen is heavier than carbon. If we look at these carbons, on the first carbon it's a tie, but if we go to the second carbon, this one has an oxygen and this one just has 3 hydrogens. That makes this side 2 and this methyl side 3. If I look at this here, okay, it goes in this direction, 1, 2, 3, like this. So 1, 2, 3 is the clockwise direction, making this R. Let's repeat again for this chiral center, this carbon here, the third carbon in. If we look here, again, the OH is 1. This time, this carbon has the oxygen attached to it, and this carbon just has another carbon attached to it, making this 2, and then just the ethyl group as 3. When I draw like this, I try to draw it away so you can see it, we again have the clockwise rotation, meaning this one is R. I want 2R, 3S. So 2 should have the OH sticking out at us, but 3 should have the OH sticking away. Said another way, when I change this from a wedged bond sticking out at us to a dash bond going away from us, this means now the H is sticking out at us, and if you could visualize, it's like you're looking at it from the other side of the paper, or said another way, the stereochemistry is opposite. So this one is R, and this one is S, and the answer is choice letter B. It's really important to practice with this because if you can't see this without practice. It can also be beneficial to make models, so it's a little easier to see as well. All right, number 2 says, which of the following is the best classification for the molecules shown below? Circle your answer. So we have enantiomers, diastereomers, constitutional isomers, or the same molecule. So the person here is showing us that we have a chiral center. But in order for these to be enantiomers, you need to have the same 4 groups attached. And here you don't. Because in this molecule, you have an OH, and in this molecule, you have a Br. So they're certainly not enantiomers or diastereomers. Diastereomers are cis and trans isomers. They're also non-superimposable mirror images. excuse me, they're not mirror images with multiple chiral centers, because the only way that's possible is if you have multiple chiral centers, and sugar molecules are common examples of this. Constitutional isomers means we have the same number of carbons, hydrogens, oxygens, and in this case bromines, but they're in a different arrangement. And if you look here, that's what we have, because in this case we have a 1 bromo 2 alcohol group, okay, here on this carbon, and so basically you have a 3 carbon chain. So this would be 1 bromo, 2 pentanol, if you will. This is 1 pentanol, so this is 2 bromo 1 pentanol. So since this Br and this OH are switched, these are constitutional isomers because we have a completely different arrangement of atoms. These are not enantiomers or diastereomers. In this question 3, we're asked to identify chiral centers. It says, how many chiral centers does the following molecule have? Remember that a chiral center is going to be a carbon atom that's bonded to 4 different things. Note that if it's only bonded to 3 different things on the paper, or 2 different things, it'll have hydrogens to make up the 4 different things. If you look here, any carbon with a double bond, which is all of them on this aromatic ring, they all have a single bond and a double bond, is not going to be chiral, because it can't be bonded to 4 different things if it has a double bond. So the first carbon we can look at is this one. This one is bonded to a chlorine, a benzene ring, this whole thing, and a hydrogen. That is a chiral center because it has 4 different substituents. If it has 4 different substituents, it can have an R configuration and an S configuration, as we talked about in question 1. If we look at this carbon right here, it's bonded to 2 chlorines. 2 chlorines are the same, so it does not have 4 different substituents. This chlorine in the benzene ring is different from this just CH group. Okay, it's a bunch of C's and H's, but it's this alkane group. They're different, but the 2 chlorines are the same. That is not a chiral carbon. If we look at this one, this carbon also has a hydrogen bonded to it that's not shown, so that'll make its 4th bond. And if we look, it's bonded to a methyl group, an ethyl group, those are not the same, this giant thing, and a hydrogen. So it has 4 different substituents. This one, it's only got 2 bonds to carbon, so it must have 2 bonds to H. If it has 2 H's, it can't be chiral because it doesn't have 4 different groups. And if we look at this one is a CH3, so if it has 3 H's, of course, it's not bonded to 4 different things, so this one's not chiral. So the answer here is there are 2 chiral centers in this molecule. Question 4 says, circle the chiral molecule from the molecules drawn below. Draw the enantiomer of the chiral molecule. Label the chiral molecule, and it says an enantiomer with the correct R or S prefix. So what we're looking for, as we talked about in the previous question, is a carbon bonded to 4 different things. If we look here, this central carbon is bonded to a chlorine, a methyl bromide, if you will, a methyl group, and a hydrogen. This is definitely a chiral carbon. It's bonded to 4 different substituents. This carbon, just to check, is bonded to 2 hydrogens. It's not 4 different substituents. It is not chiral. This carbon is bonded to 2 methyl groups, an ethyl group, and a bromine. This is again not chiral because it's bonded to 2 methyl groups. Now that we've drawn this, or we've identified this, we need to draw the enantiomer. And it turns out that I'm going to argue that it would be slightly easier to draw the enantiomer first and then to determine if it's R or S. So to draw the enantiomer, I'm going to switch any 2 groups. Well, how am I going to decide which ones to switch? Well, the way I want to switch them is I want to switch this hydrogen and this chlorine. Because if I switch the hydrogen and chlorine, the hydrogen will be pointed away from me, and then whatever I get is the correct chirality. I don't have to worry about switching it in my head or anything like this. So I'm going to redraw this. This is just this carbon. Okay, it's going to be bonded to this chlorine, because now I'm switching these. This hydrogen, which is now pointing it away from us. This methyl bromide, if you will, group, CH2Br, which is pointing out at us, as is shown here. And this CH3. Now, this serves the purpose of drawing the enantiomer. If you switch any 2 groups, note that you can only switch 2, all right? If you switch any 2 groups, you'll have the enantiomer. You have to. The only way you can see this is to build models, all right? It takes a lot of practice to be able to see these things in your head. Now that I've done this, I can go ahead and assign priority labels because it's going to be easier to identify this one and then this one as RRS, and then this one's just the opposite. So here, my one priority is my chlorine because it's more massive than the carbons. CH2Br is going to be more massive and a higher priority than CH3, and CH3 is going to be last. Note that I talked about how we assign these groups a little bit more in question 1. So now we have 1, 2, 3. So we're going in that direction. Okay, 1, 2, 3 in that direction. If you notice here, this is the clockwise direction. So since this is the clockwise direction, this is the R enantiomer. By definition, this one must be the S enantiomer. Again, if you switch any two groups, all right, we switched, this chlorine went here, this H went here, you will get the opposite enantiomer if you have a chiral center. Note that you can only switch two groups. If you switch more than two groups, you can switch it back, okay? So I don't want to talk about that too much, but only switch two groups. In this case, I switched these two groups for convenience. Now I have the H away from me. It's easy to identify whether it's R or S, and then the other one has to be the opposite. All right, this question is kind of just memorization. It says, which of the following compounds is acetone, a ketone, a commonly used solvent used to clean glassware? So if you look here, there is only one ketone. This is the only ketone. C double bond O, methyl group, or R group, two carbon containing groups. This is the only ketone, and acetone is a ketone, so this is the right answer. This molecule has a functional group of an ether, and this one is diethyl ether, commonly called ether. All right, because you have a CH2, CH3 on both sides, so diethyl ether, again, commonly called ether. This molecule here, C double bond O bond OH, is carboxylic acid. This one, with a CH3C double bond O bond OH, is acetic acid, the stuff you would find in vinegar. And finally, this molecule here has a C double bond O and then a carbon containing group instead of an H. So this is a carboxylic acid. This one is called an ester. This here is acetate. So this was acetic acid. If we take that H away, that's acetate. So this is acetate. And we have a CH2, CH3, or an ethyl group. So this one is ethyl acetate. So acetone, which is one ketone, is this one, and this is the only ketone. So you have a 3-carbon chain, ketone in the middle, and 2 methyl groups on the outside. That one's called acetone. There's no good way for me to tell you other than to try to identify the functional groups if you're not sure which one that it is by memory. All right, number 6 says, a student is performing an acid-base extraction on unknown compounds, and they extract the organic layer with 5% sodium bicarbonate solution and separate off the aqueous layer. Next, they add hydrochloric acid solution to the aqueous layer and observe a white precipitate. Which of the following compounds would most likely be in the precipitated compound? All right, the answer here is carboxylic acid. So if we have a carboxylic acid, C double bond O bond OH, and we add to this sodium bicarbonate, NaHCO3. I'm going to focus on what happens to the organic thing and not the byproducts of carbon dioxide and water. But effectively, what happens is this is a base, so it's going to remove this proton. What we're going to end up with is C double bond O minus, Na plus, because Na is the counter ion here. Okay, you're going to get H2CO3 as the byproduct, but H2CO3 is not stable and it breaks down into carbon dioxide and water. The interesting thing here is if you have this in the organic layer, okay, in this case, it doesn't say what the organic layer is actually. When we add this 5% sodium bicarbonate, it's 95% water. And this is the sodium salt of the carboxylic acid. So assuming that this is a large organic group and it's not soluble in water because it precipitates, okay, this molecule becomes aqueous. If we want to get this back, what we do is we add H+. So we drain off the organic layer. We drain off the aqueous layer and separate it from the organic layer. So now there's no more organic layer. We add H+, and we reprotonate the carboxylic acid like this. But this carboxylic acid is not soluble in water, okay, because it has a bunch of carbons here that are not shown, so it becomes a solid and it precipitates. If you have an ether, nothing will happen. An amine, you can extract it, but you need to use a base. Excuse me, you need to use an acid followed by the base once it's in the aqueous layer, and an ester, nothing will happen. So carboxylic acid is the correct answer to this question. All right, so in the previous question we talked about what happens when you add bases to carboxylic acids. In this case we talk about what is happening when you add acids. So number 7 says, which of the following molecules will have appreciable solubility in an aqueous solution of 5% hydrochloric acid at room temperature? So carboxylic acids, okay, with large organic groups, are not going to be soluble because when they're protonated, they're not soluble in water. Here you have the sodium salt of a carboxylic acid. Believe it or not, this would be soluble in water. Actually, this is a common preservative that you would find in, soda. All right, this is called sodium benzoate. However, this isn't going to be soluble in 5% hydrochloric acid. Why not? Because we're going to put an H here, okay, and then once we have an H here, it'll be the same as this molecule, and it won't have solubility in water. How about this one? This is an ester. Esters, large esters like this, are not going to be very soluble in water. Adding an acid isn't going to help that, so it's still not going to be soluble. What about this molecule? In this case, we have an amine, and you'll note that this amine has a lone pair on nitrogen. So if we add an H plus to this, and this grabs this, what we end up with is an H here. All right, I'm being lazy and not redrawing it, and a plus charge on nitrogen. The counter ion in this case would be Cl minus. This molecule is now a salt, and this salt is aqueous. All right, if you go to CVS, a drugstore, you can see several amine salts that are available as prescription and even non-prescription medications. And the reason they make the hydrochloride or hydrobromide salts of these things is to make them more soluble in water. There may be other reasons due to their stability in air, but one reason is that they're more soluble in water. So the answer here is A. You need an amine to react with the hydrochloric acid. All right, so the last question says, fill in the blanks in the separation scheme below. You may use any of the given reagents, acids and bases, states of matter, or the compound shown in the beginning of the separation scheme to fill in the blanks. There are 4 blank spaces in the separation scheme that you would need to be filled in, worth 5 points each. Okay, so that's basically that. So what we have is benzoic acid, which is this one, biphenyl, which is this one, and benzocaine, which is this one. So this one, not surprisingly, is a carboxylic acid. It's called benzoic acid. This one is an organic base. These two molecules are both neutral. I'm just going to write it as N. So these molecules are both neutral. We have all of these molecules dissolved in ether, and we're going to extract with aqueous something, and we're going to get carbon dioxide and water. Now, you need to be aware, and for safety reasons, I think you've been told this a bunch of times, that when you add acids to sodium bicarbonate, you get H2CO3, which is not soluble in water. So H2CO3 readily decomposes into CO2 and H2O. And if you add them up, this two H's and an O would leave CO2. So this is this, and this is not soluble at atmospheric pressure and temperatures. So basically, this carbon dioxide and water tells us that we must have added 5% aqueous NaHCO3. Now the question becomes, which of these molecules will the 5% aqueous NaHCO3 pull out of solution? And as we talked about in question 6, bases react with organic acids. And what you're going to end up with is this compound, C double bond O minus, Na plus, the sodium salt of, sorry, there's no methyl group there. I was thinking there's a methyl group there. The sodium salt of benzoic acid, which is now soluble in water because it's an ionic compound. Now in the organic layer, you're going to have hidden compounds 1 through 3, which is going to be your biphenyl, your benzocaine, and your phenol, because none of these compounds are going to come out of the ether. And then you're going to have trace of something. Well, if you add aqueous sodium bicarbonate, you're definitely going to have traces of water in your organic layer, and this is why at the end we typically add drying agents before we dry up the ether. Now what happens? We take this molecule here and we add 6 molar HCl and vacuum filter. We get an aqueous, which is NaCl and water, and a solid. So if we want to get this to precipitate out of the aqueous layer, we need to turn it back into benzoic acid. And again, as we talked about in question 6, in order to do that, adding 6 molar HCl is an effective method. It reprotonates this minus charge here, so in the acid, it gets the proton back. This molecule is now not ionic and not soluble in water, so it precipitates. So this is how we can best fill in this separation scheme. Note that if you did not use the thing in the lab ever, it's probably not the right choice. So for example, H3PO4, you never use phosphoric acid for anything. You never used anhydrous magnesium sulfate for anything. Arguably could be used. You never used acetic acid for anything. So don't pick ones that you never used before, because they're probably not going to be the right answer. All right, well, I thank you for watching this. I hope that you found it helpful, and you guys are doing awesome, so keep up the hard work.